we have a gap. Okay, we have a gap. So when we start putting heat in, right, like free expansion. So when there's a gap, means there's free expansion. Okay, so you don't see any stresses at all. Okay, like what you see over here. You don't see any stresses at 0.5, 0.4, 0.3, 0.2, 0.1. And once it reaches zero gap, there you see stresses. Okay, now the previous part when I started over here, right? Let's say the question did not have any gaps at all, right? Stresses will start to build up over the thermal expansion length of what? 1.347 times 10 to the power minus 3. Okay? And then when the gap is at 0, now when there's a 0.5 gap, so this case, right, you will not get any what? You'll not get any stresses yet when you increase the heat. Then when you slowly increase the heat, when the gap is equal to 0, that's why you minus the what? 0.5, then you see what? Stresses. That is where you have to compensate the what? You have to compensate for the gap on your delta T. Okay? Are we okay or still not very clear yet? That's why I wrote down here. That's why I draw this graph. Okay, that's why I draw this graph. Right? No stress, no stress, no stress. So over here, right? The gap is getting smaller, 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 smaller. Once you see 0 stress, then you get what? Then you get a stress. Okay? Right. Anyone, any question? I will dwell on this. Okay. Anyone, any question? If you have question, please ask me, please. Thank you. So if zero gap thermal, so what I'm trying to say down here is this. Okay. Let's say the question, okay, let's say the question says that there is no gap. Okay, so let's say the question say, okay, people, there is no gap. Okay, so when there's no gap, right, when the structure start to change its length, when the temperature start to increase, you will see stresses over a free expansion of 1.347. Okay, now when there's a gap, right, you don't see when there's a gap now, right, the thing will start to grow. Right, when the things start to grow, you don't see any stresses. But when the gap is equal to 0, eventually this gap will be equal to 0, right? Eventually this gap, right, over when you increase the temperature, the gap will 0. Then you will see stresses. That's where you have to compensate out for the what? For the minus 0. What? For the minus 0.5. Okay? Okay, so to Jerome's question, if zero gap thermal stress is equal to 1.3, yeah, when you have no gap. But when you have 0.5 gap, you have to take off the 1.3 minus the what? The 0.5. Okay. Right. So now, okay. So step 2 now. So we have done step 1. Okay. No restriction. Then we calculate our thermal stress. So step 2. Right. Step 2 is for the redundant load. Okay, we're going to calculate the redundant load. Okay, so now I'm going to draw the same diagram twice. So this is for. So now our gap is 0. Okay, so this is A and this is B. Right, so I'm going to divide my page into 2. Okay, so for this case, we are going to focus on aluminum. Okay, and for the other side, we're going to focus on the steel. Okay. So for the aluminum, when it's touching, you have a redundant load during compression. Okay. So this redundant load, so this is R for aluminum, right? So when it touches the steel, right, you have a reaction, and this will push the aluminum into what? Compression. And then if we look at the steel, same thing. Okay. So this redundant load, what if for the steel? Okay. So redundant load for the aluminum, right? So for both of them, at the state of equilibrium, okay, of the state of equilibrium, right? The redundant load for aluminum has to be equal to the redundant load of steel. Okay. And both redundant of aluminum will induce compression on aluminum, right? RAL will induce compression on what? This is your wrong thing to do the same shading. This is for aluminum, right? This is your aluminum, right? So reaction on aluminum will induce what? Compression. Then if you look at your steel, right? This is your steel. The RST, right, will also induce what? Compression. Okay. Right? So both will induce compression on aluminum, and R of steel will also compression of steel. Okay. So basically, is action equal to what? Reaction. Same in magnitude, different in direction. So this is based on, so when you make the assumption, this is based on Newton's what? Third law. Okay, but both will induce what? Compression. Okay, so focus. So if you look at the aluminum, focus on the aluminum, it induce compression. You focus on the steel, you also induce what? Compression. Okay, so for this case, I'm going to write out. So how? So what we're going to calculate now? Okay, so let me put it on the side. So we're going to calculate deflection induced by the redundant load. Okay, so we know, right? So we know that the redundant load R of steel is equal to R of aluminum, and I'm just going to call it as what? R. Okay, so deflection due to the total redundant, or deflection due to the redundant load. Okay, so minus R. Okay, minus R. Why minus R is in compression. Then L. So now I'm going to focus on aluminum. So L for aluminum is 0.3. Divide by cross-sectional area is 2000 times 10 to power minus 6. And then the Young's modulus is 75 times 10 power 9. Okay, so this is for aluminum. Right, because it's going to induce, why minus? Because it's going to induce compression. So sorry, the formula that we are going to use, I'll just write down here, it's easier for you, is equal to RL over what? AE. Okay, then plus again minus R. Okay, And then this, we're going to look at the stainless steel now, 0.25 or the steel, right? And then we're going to divide by the cross-sectional area, which is 800 times 10 to the power minus 6. And the Young's modulus is equal to 190 times 10 to the power 9. So over here, this is for your stainless steel. Okay. So from here, this will be equal to 0.3 divided by 2000. 0.3 divided by 2000 power minus 6 divided by 75 power 9 is equal to 2 minus 2 times 10 to the power minus 9 R. And then minus again, so 0.25 divided by 800 power minus 6 divided by 190 power 9 is equal to 1.645 times 10 to the power minus 9 R. So this will be equal to 2 power minus 9 plus by 1.645 power minus 9. So it's equal to 3 minus 3.645 times 10 to the power minus 9 R. Okay, and then lastly, we're going to, not lastly, we're not done yet. Yeah, so we're going to do delta T due to heat plus by delta due to the redundant load. The whole thing will be equal to what? 0. Okay, so the deflection due to temperature is 0.847 times 10 to the power minus times 10 to the power minus 3. Is it times 10 to the power minus? Yep. Then plus by delta R is equal to minus 3.645 times 10 to the power minus 9 R. So the whole thing equals 0. So therefore R is equal to 0.847 times 10 to the power minus 3 divided by 3.645 times 10 to the power minus 9. Okay, so 0.47 power minus 3 divided by 3.645 power minus 9. So it's equal to 232. So what I got is 232.373 times 10 to the power 3 Newton. And then the redundant load we know will be in what? This load is going to induce what? Compression. Right, I told you, right? When temperature increase, you get what? Compression. Okay, so we're going to calculate. So we have calculated. So what have we calculated? So this question asks for what? This question asks for the normal stress in the aluminum. Okay, so we're going to calculate the normal stress. Part A. Normal stress of the aluminum. Okay, so we are going to focus on stress aluminum. So the force we calculated is what? The force we calculated is 232, right? 373. Right, 232.373, right, times 10 to the power 3. And you know that it's going to be minus because it's in compression, right? And let me write this better or not, you guys get confused. Okay, and then divide by the cross-sectional area. So the cross-sectional area is 2000 times 10 to the power minus 6. So this will be equal to minus 232.373 power 3 divided by 2000 power minus 6. So it's equal to minus 116.1865 times 10 to the power 6 Pascal. Okay. And then for part B. So part B asks for the change in length